Okay, we're going to do problem 220 now. This time we're going from velocity graph to position graph, so we want to look at a different characteristic of the motion. We're also figuring out total displacement and average velocity. Those will be easy to do once we've drawn the position graphs. So instead of looking at slopes here, we're looking at areas. The area under the velocity graph is going to tell us the displacement. We have to either be given the initial position or make it up, because that information is not in here. But what we can find is where we go from there. So in this first second, there's no displacement because we have no velocity. So I don't go anywhere for a second. However, in the second section, the area here is the height of this rectangle, which is the velocity, which is 3 meters per second, times the amount of time that happens. That's 2 seconds. So 6 meters is the displacement, which means my change in position from 1 second to 3 seconds is 6 meters. I started at 2, which means I must end at 8 for a delta x of 6. I know it must be a line because the velocity is constant at CVPM. The position graphs are always linear. Okay, if I look at the area in the third section, the height of this rectangle is -1 meters per second. That's the velocity, times 2, 4, 6, 7 seconds, giving me a displacement of -7 meters, which means I started at 8. I need to end at 1 at the end of that time interval. So it will look something like that. Okay, now the displacement is final position, which is 1 meter, minus initial position, which is 2. So -1 meter. It all happened over 10 seconds, so the average velocity is, again, this slope of this line connecting the beginning to the end. It's also the displacement over the total time, which would be -0.1 meters per second. There is a direction change here. Right there, we go from positive to negative velocity, which is what you see on the graph there. Alright, so over on the next one, same thing. We're looking for the displacement by finding the area under the velocity graph. In the first section, the height of that rectangle, which is the velocity, is 1 meter per second. And that goes for 6 seconds, which means we have a displacement of 6 meters during that section. If we started at 1, we have a displacement of 6 meters. We need to go to 7. We know it's linear because it's CVPM, because the velocity is constant here. So this is a constant positive slope. This is a constant positive value. That's how the relationships works. We can go backwards with it just as easily as we can go forwards. Next section, no velocity, no displacement. So the position will not change. And in the final section, the height of that rectangle is -1 meters per second. That's the velocity times 2 seconds. So the delta x equals -2 meters. I started at 7. Which means I will end at -5. So the total displacement, I'll end at +5. The total displacement, I go from 1 to 5 meters at the end. So xf minus xi is 5 meters minus 1 meter, which is 4 meters. The average velocity, delta x over delta t. Also the slope of this line, 4 meters in 10 seconds, 0.4 meters per second. There is also a direction change here. We go from forward to stopped to backwards, so across this area we change direction.